Hello, featuring learners, subscribers, viewers, and students. Here is the last video, the last solution presentation to this beam problem, which I solved in this the eighth way by the matrix approach. So you may also look at the seven solutions I presented to this problem if you want to master deflection problems in beams. So here we go. The beam is subjected to the loads shown. If EI is constant, determine the slopes and deflections at points A, B, C, D, and E by the matrix approach this time. So the stiffness of a member is derived in matrix structural analysis. So for those civil engineering students out there, if you want to know the stiffness of the member, then this is the stiffness of the member. 12 EI all over L cubed in the first row, then 6 EI over L squared. The negative of this cell, negative 12 EI over L cubed. Then you just copy 6 EI over L squared. The second row would be 6 EI over L squared, 4 EI over L. Then the negative of this cell here, then half of this cell value 2ei over L. The third row will be the negatives of the first row. At the figure, look at the stiffness of the member. And the last row, we just copy second row except that we interchange the second and the fourth cell values. So 4ei over L now is here and 2ei over L is here. So that will be the guide. Now, for this beam, A, B, C, D, E, at A there is 1 degree of freedom, at B2, C2, D1, and at E2. 2 means we have deflection downward and rotation. At supports only one, just the rotation. So with the restriction or the limitation of your high-tech calculator, it's only 4x4, so this is the plan. We consider first A, D, and E. So one unknown here, theta A, one unknown here, theta D, and two unknowns here, deflection at E and the rotation at E. So we can manage to solve those slopes and deflections at the stated points. And after we know this, then we can now consider A, B, C, D, and we have two remaining unknowns, two at B, two at C, and two known displacement slopes at A and B. So we can use the partitioning method to do that. So that's the plan. So first we consider ADE, and therefore the friction moment at A, which is represented by this, the friction force, not important because this is a support. It cannot displace the support because the support is the supports are unyielding at this given problem. So we have to consider the strip. Then we have a triangle here. The height of the strip is denoted by W, and therefore this is W minus 15 kilonewton per meter. So W means 15 kilonewton per meter as to X. So I designate this as X equals 30 minus 15. So 15 as to 3. So W therefore is 5X plus 15. So the friction moment at 8 for AD, I'll just call it AD because we consider ADE, is the integral formula is PA d squared over L squared, negative, but it is now represented by this sense, counterclockwise. Remember from slope deflection equation, clockwise is positive. So since this is counterclockwise, that's the sense. Integral of differential P, so the differential area of the strip, W dx, so W dx, and that's differential P. A is its distance from point A and it is equal to 6 meters minus x. Then b squared is the distance of the street from D, which is x plus 3. So quantity square all over L squared, the length of AB is 9. Then the fixed moment of this concentrated load is 12, A is 6, B is 3, so 6, 3 squared all over 9 squared. And the value of the integral is 75.75, while the value of this is 8. Therefore, combining, that's 83.75 kilonewton meter. While fixed moment dA due to the varying load is integral of W dx, then we just square interchange squared factor. So this is now squared, and this is just x plus 3 all over 9 squared. So from 0 to 3, the integral is 70.5. Then while the fixed moment of this 12 kilonewton load is 12 times 6 squared times 3, interchange squared term, just like here. So it is all over 9 squared, so it is 16. So combining, that's 86.5 kilonewton meter. Therefore, these are now the net nodal loads at A, which is node 1, at D, which is node 4, because this is 2, 3, and at 5, we have 15 kilonewton downward only. So these nodal loads are opposite to these fixed end forces. So since this is counterclockwise positive, this is now the load which is clockwise, and the value is the same. So this is a negative load because it is clockwise. Then at B rather, this is clockwise, so the load is counterclockwise, 86.5, and finally at E, just copy the load, 15 kilonewton downward. So the stiffness of AD, substitute into this member stiffness, elemental stiffness, is 12. EI is factored out because it is constant. Then 12 divided by 9 cubed is 4 over 243. 6 over 9 square is 2 over 27. The negative of the first cell, copy the second cell. Then 6 EI over L squared, so it's the same. 4 times 1 over 9, so 4 over 9, the negative of that cell, and this is half of that cell value, 2 over 9, then the negative of the first row, copy the second row except that these cells interchange position. So that's it for stiffness of AD. For DE, it is EI, quantity 12 over 2 cube, 1.5, 6 over 2 square, 1.5, then the negative of that cell, then you just copy, then 6 EI over L square, so 6 over 2 square is still 1.5, 4 over 2 is 2, over 4 times 1 over 2 rather, then the negative of that cell, then half 1, and copy negatives of the first cell, and copy the second row, interchange these two cells here. So that's it. By the way, the numbering, this is 1, 2 for node 1 or A, then this is 7, 8. So we have 1, 2, 7, 8, 1, 2, 7, 8, then DE 7, 8, 9, 10, 7, 8, 9, 10. Then we are only interested of the displacements at 2, theta A, at 8, theta B, then at E, delta E, and theta E. So these are the nodal forces. Factor of EI, which is common. Then we have 2, 2, 2, 2, you add 4 over 9 only. Then 2, row 2, column 8, 2, 8. So we have 2 over 9. Then 2, 9, there's no 29 there, 0. 210, there's no 210 there, so 0. Then we just copy because the matrix is symmetric. So we can just copy 2 over 9, 0, 0. This is 8, 8. So 4 over 9 plus 2. So that's 22 over 9. 8, 9, 8, 9, negative 1.5, 8, 10, 1, 10, and so on and so forth. So this is the overall stiffness matrix. Then we can now compute these displacements, U2, U8, U9, U10, U2, U8, U9, U10, specifically theta A, theta B, delta E, theta E. So E is 1 over EI, factor this out, 1 over EI times the inverse of this matrix, let's copy, times this force matrix, this force matrix here. So using your calculator, these are now the results. So this is force matrix equals overall stiffness matrix times displacement vector matrix. So that's why we have here the results, theta A, theta B, delta E, theta E. So using your high-tech calculator, capable of solving 4x4 simultaneous linear equations, and these are the results. So by matrix approach, of course. So theta E is negative 336 over EI, theta D 295.125 over EI, delta E 550.25 over EI, and theta E 265.125 over EI, just like the values in the previous 7 methods. So since we already know the displacements at A and D, so we now consider displacements at B and C, considering A, B, C, D. And take note that AB has a length 3, BC 3, and this is also 3 from the previous slide. So this is 3 meters. So therefore, and because EI is constant, the stiffness of members AB, BC, CD are equal. They only differ in the numbering. So KAB, for example, is 12, EI factor out, over 3 cubed this time. So 12 over 3 cubed is 4 over 9. 6 over 3 square is 2/3. Then the negative of the first cell, then we just got the second cell. Then this is 6 over 3 square, so 2/3. 4 over 3, 4 times 1 over L, 4/3, the negative, and half of 4/3, 2/3. Then the negative of the first row, then copy the second row, we interchange second and fourth cell as shown. So that's for AB. This is for BC. The numbering for BC is 2, 3, 4, 2, 3, 3, 4, 5, 6. And lastly, for CDEI times the numbering 5, 6, 7, 8. And the elemental stiffness, the same. Then for the fixed moment this time, for AB, there's no load. CD, no load also. So we focus on BC. So for BC, we imagine B and C are fixed, and the loadings will be composed of this rectangular loading and triangular loading. The 12 kilonewton load acts at the fixed end, so it has no fixed end moment, but we incorporate it to solve for the reactions at the support supposedly, which is at C. So fixed moment for BC, this is the sets counterclockwise, at C clockwise due to the effect of these loads. So at B, it is due to this uniform load WL square over 12. So 15, 3 square over 12 plus due to the triangular load WL square over 20. So 15, this is also 15, 30 minus 15, 3 square over 20, and therefore combining that's 18 kilonewton meter, this fixed moment DC. Then for fixed moment CB, it is WL square over 12, 15 3 square over 12, plus the contribution of this triangular load, WL square over 30. So 15 3 square over 30, 15.75 kilonewton meter. We then solve this FB here. So summation moment C equals 0. FB times 3 plus fixed moment CB, 15.75 equals fixed moment BC, 18 plus the moment of the rectangular loading, 15 times 3 times 1.5 plus the moment of this triangular loading, 1/2 of 3, 15 times 2. So solving for that, force 38.25 kilonewtons. Likewise, we sum up moment about B, F sub C times 3 plus fixed moment BC, which is 18, then equals fixed moment CB, 15.75, moment of the rectangular loading, 15 times 3 times 1.5, plus moment of the triangular loading, 1/2 of 3 times 15 times 1. So F sub C is 41.25 kilonewtons. Therefore, the nodal load at B would be the opposite of these fixed forces. So we have a downward load of FB, which is 38.25, and moment couple of opposite to this counterclockwise, so clockwise, 18 kilonewton meter. At 3 or C, we have downward load of 41.25, and opposite to this moment is counterclockwise moment, 15.75 kilonewton meter counterclockwise. So this is clockwise negative, downward negative, counterclockwise positive, downward negative. So the force, the stiffness, structural system stiffness for ABCD therefore is negative 38.25 downward, then negative 18 for this is F3, F4, then F3, F4, then F5, negative 41.25, F sub 6 is positive 15.25, then F7, F8 known, F2, which is at A, then F8, which is at D, that's F2 and F8, which are known. So we then partition. So the numbering, the unknowns, 3, 4, 5, 6, then 2, 8. Then we have to compute these cells. 3, 3, for example, is 3, 3. So we have 4 over 9 plus 4 over 9 is 8 over 9. Then this is 3, 4, 3, 4, negative 2/3 plus positive 2/3, that's why it's 0 here. 3, 5, 3, row 3, column 5, 3, 5, negative 4 over 9. Then 3, 6, 3, 6, 2/3. Then 3, 2, 3, 2, negative 2/3, and 3, 8, 0, there's none. And we copy by symmetry here. Then this is 4, 4. I will not continue. I'll just give you some examples. So 4, 4, 4, 4. We have 4/3 here and 4/3. So 4/3 plus 4/3, 8/3. 4, 5. 4, 5, we have negative 2/3 here. Then 4, 6. 4, 6 is 2/3. 4, 7, 4, 2. 4, 2 is, we have 4/3 here. 4, 2, 4/3. And 4/2, sorry. 4/2 is 2/3, so that's why you have 2/3 here. And 4/8 is 0. And so on and so forth. We know already this as students in matrix. Then the displacement at 2 is negative 336 over EI or theta A, already computed in the preceding slide. And theta D is 295.125 over EI, also calculated in the preceding slides. So we expand. So this force matrix here equals EI times this force matrix 4x4 stiffness matrix here, part of the stiffness matrix, times this unknown displacement. So I'll call this K1 and this one K2. So K1 times this unknown displacement matrix, K1 times this unknown displacement matrix, and I call this K2, this 4x2 matrix, times this 2x1 matrix. So 4x2, 2x1 would be 4x1. So for instance, this matrix K2 times this matrix here, negative 2/3 times negative 336 over EI, that would be, so because there is EI here, cancel EI, negative 2/3 times negative 336 is 224, plus 0 times 295, so 224. 2/3 times negative 336 plus 0 times 295 is negative 224. Then 0 times negative 336 plus 2/3 times 295.125, that's 196.75. 0 times negative 336 plus 2/3 times 295.125 is 196.75. We now combine this conformable matrix with respect to addition or subtraction. So negative 38.25 minus 224 is negative 262.5. Then negative 18 minus negative 224 is 206. Negative 41.25 minus 196.75. Negative 238, 15.75 minus 196.75 is negative 181. Therefore, we can now compute these unknown displacements U3, U4, U5, U6 as the product of the inverse of this matrix K1, which is this, and this simplified force matrix after we combine these two. And therefore, since U3, U4, U5, U6 are respectively delta B, theta B, delta C, and theta C, we can now compute that with your high-tech calculator. So delta B is negative 847.5 over EI, theta B negative 175.5 over EI, delta C negative 823.125 over EI, and theta C 187.875 over EI. So that's it for this video.